In this unit, we're going to be studying the force of gravity. We probably usually think of gravity as that thing that pulls us down. But there's got to be more to it than that. What direction does the sun pull the earth, or the earth pull the moon? What direction do those things pull you? And why is it things like planets and moons and stuff that seem to have gravity? Do we have gravity? Do everyday objects have gravity? It turns out that gravity is actually a force between every two objects that have mass in the universe. It's a universal force that affects everything. And that's what this unit's going to be about, to try to understand how that universal force works and to try to make some sense of its patterns. We've learned about a lot of forces this year, but we understand force now to be caused by four fundamental interactions, and that a lot of the forces we see are special cases of these four. The four are gravity, electromagnetism, and then two forces that act in the nucleus between protons and neutrons and the particles that make them up, called the strong nuclear force and the weak nuclear force. Everything else is a special case of those four forces. For example, normal force is actually an electromagnetic force. When you stand on the ground, your electrons are being pulled into the ground by gravity, and the ground's electrons are saying, no, your electrons are not coming here. And we experience that as the normal force. But really everything is just an example of these four. And strangely enough, gravity, the thing we all grow up learning to live with and live in, is the force we understand the least. The current best understanding we have of gravity comes from Albert Einstein's theory of general relativity, which he developed roughly between 1905 and 1920. It has really good explanatory power. It's also super mathematically complicated. So we're going to start with the earlier theory of gravity, come up with by Isaac Newton and published in 1687. Einstein's rules for gravity explain a lot more about where gravity comes from and why it acts like it does. It also explains certain sticky situations Newton's law doesn't do a good job with. It's still worth learning Newton's law, though. Although we're constantly trying to figure out the why do things behave like they do, and general relativity doesn't fully get us to where we need to be on that. But sometimes we're more interested in just making predictions and getting a good enough answer for how something's going to behave. And we're not quite as interested in the whys or the origin of the theory. And that's where Newton's law of universal gravitation is still useful. Einstein's replaced it, but this law is a lot mathematically simpler, and it can get you what the acceleration of gravity is on different planets. It can help you predict orbits. It does a lot of stuff, and therefore it still has use to us. There's a lot of theories in science that we no longer think are exactly what nature's doing, but still have use, and we keep them around. VSEPR theory in chemistry. That's when you do like sp3 orbitals and stuff to figure out why molecular geometry is what it is. That's been replaced by something called molecular orbital theory, which does a better job explaining all molecular shapes. But it's complicated. If you can do it with a simple rule like VSEPR, and it works for a lot of things, it's worth knowing it, and you just use the more complicated stuff when you need to. We have things like this in physics too. When we study springs, we use something called Hooke's law. Hooke's law works for a lot of springs, but not all. It's useful for the one it works for, though, because other rules are more complicated. Lastly, Ohm's law, the relationship between voltage or electron pressure and current that is taught in almost all introductory electronics classes. It fails for some devices, but for the ones it works for, it's very helpful. So that's why we're sticking with this old 1687 law and why it's worth learning. Let's look at Newton's law of universal gravitation. Here's the equation for it. And as I said before, Newton's law is that every two objects with mass in the universe attract each other. The equation shows what matters. The big G here is a constant, kind of like pi. It's in the equation, it's just a number, and it's in every Newton's law calculation there is. M1 and M2 are the masses of the two objects. We can see that the force of gravity will be bigger if M1 or M2 is bigger. And that might be the explanation of why we feel the Earth pulling on us, but we don't feel the person sitting next to us pulling on us. The Earth's mass is really big, so maybe one of these masses has to be big for us to notice. The D on the bottom stands for the square distance between the two objects. A lot of times this D is written as an R, and I'll show you why. So what I've got here is a picture of me, and I'm putting a force of gravity on a box that's a distance R away. You can see that I've drawn circles spreading out from myself towards that object. The object is on the outermost circle, whose radius is the distance between me and it. We're going to see that that's how the law of gravity seems to work. So that's why R and D sometimes get substituted for each other as the distance on the bottom of Newton's law of universal gravitation. So just be careful about that difference in naming. The thing on the bottom of this equation is the distance between the objects who have mass 1 and mass 2. R and D mean the same thing. They do not mean radius and diameter. There's going to be a series of lessons we're going to go through. The first one is going to be to try to explain why the thing on the bottom is distance squared. This is called the inverse square law. We're then going to talk about what big G is and how it was discovered. Finally, we'll talk about how we can use this equation to figure out what the acceleration of gravity is in various places and to calculate various forces.